Okay, these notes are going to be on page 89, and today's lesson is going to be on trends with atomic size. Okay, so moving forward, we've talked about the development of the periodic table and different groups in the periodic table, and those groups having similar properties. The rest of these lectures are going to be about, okay, can I talk about different trends based on the way the periodic table is set up by increasing atomic number? And the answer to that question is yes, you can. Okay, so by the end of this lesson and in class practice, you should be able to explain to me how the atomic radius is found, and then describe to me the periodic trends and how they relate to the atomic structure of the elements. Okay, now think about this, if you will, with me, about what an atom looks like, okay, how we developed our image of an atom. Okay, now if you remember, our last kind of image of the atom has protons and neutrons inside of the nucleus, and then this kind of like electron cloud outside of the nucleus. Okay, so with that being said, I can't take a measuring tool from the inside of the atom in the nucleus to a fixed point on the outside of the atom. Why? Because I don't know where the outside of the atom is, because the electrons are moving so fast. I can't say where those electrons are to kind of figure out how big that atom will be. Okay, so we say that atoms don't actually have a fixed radius, okay? The radius of an atom is going to be found by measuring the distance between two nuclei of touching atoms. Okay, so let me write down a couple of definitions here for you. Okay, so the radius of an atom is found by measuring the distance between the nuclei of two touching atoms. Okay, so you can kind of see my image here. I have two bromines together. So I can measure from one nucleus of a bromine to another nucleus of a bromine, and if you remember, half of a sphere is r, which is the radius. Okay, so if I have 2r, that means that there's two radiuses present. So then I can actually talk about the radius of one atom. Okay, does that make sense? So the atomic radius is actually going to be half of the distance between the nuclei of two atoms, okay? And that's how we actually measure it. I can't find the radius from one atom. I need to find the radius of two atoms that are touching. So here's our definition. Half the distance between the nuclei of two like atoms is going to be the atomic radius for one atom, okay? So if I have the distance between two like atoms together, between their radius, I can divide that by 2 to figure out the radius of one atom, okay? And that's actually how we measure the size of atoms. Now, I can only do that if the atom is the same, right? Because if I'm finding the distance between two different nucleuses, or nuclei, sorry, that's the word, nuclei, I'm not going to be able to find an accurate radii because the r is not similar. Therefore, I'm changing the variable. Okay, so since we have a periodic law, and since we have similarities and differences between groups and periods, we can start to talk about the trends of atom size based off of the periodic table. Okay, so let's talk about the group trend first. This one's a little bit more easy to understand than the period trend. Okay, so as I move down a group, so let's look at group 1, for example. As I go from hydrogen to francium, the size of my atom is going to get larger, okay? So francium is a much larger atom than hydrogen is, okay? And let's kind of think about why, based off of electron configurations. If I was to compare lithium and sodium, sodium has one more energy level than lithium does, okay? So if I look at this, lithium's last electron resides in 2s, where sodium's last electron resides in 3s, okay? Since sodium has a 3s orbital, that means it has an extra sphere around its nucleus, which is going to make it bigger, okay? Where lithium ends at 2s, so it has one less orbital, which will make it smaller, okay? That's a little bit easy to understand. Period trend. So as I move from left to right, so as I move from, let me show you here, from say lithium to fluorine, the size of my atom is actually going to get smaller. Okay, now let's talk about why this is. I can't talk about different energy levels. Why? Because lithium and fluorine's electrons are in the same energy level. Okay? Lithium and fluorine's electrons are both in the 2 energy level. 2s for lithium and 2p for fluorine. Okay? So I kind of have to talk about something different then, if their electrons are all in the same energy level. So I have to talk about how many protons are inside of the nucleus of the atom. Okay? The more protons that are inside of the nucleus means I will have more attraction to that center. Meaning, if I have electrons outside floating around, okay, and there is a more positive charge in the center, those electrons are going to want to be closer to the center of the atom, okay? So as the number of protons increase across a period, there's more attraction from that negative to the positive inside of the center. More attraction equates to smaller atom, okay? That's the period trend. And we'll talk a little bit more about that in class because I kind of have a little trick to help you remember that. Okay, last thing that I need to talk about with size is this thing called the shielding effect. Okay, as you move down periods, so like from period 1 to period 7, the trend for size getting smaller across the period is going to be less pronounced. Okay, and this is due to this thing called the shielding effect. Okay? What's happening here is the inner electrons are kind of hogging the positive force to the electrons that are on the outside. Okay? What does that mean? It means that the electrons that are all the way out in the highest energy level can barely feel that positively centered core, because the electrons that are closer to that positively centered core kind of hog the force, okay? So let's kind of think about this for a second, but let me write the definition for you. So the inner electrons hog the attraction of the protons from the outer electrons, and because of this, the electrons on the outside don't feel as much pull from the protons or as much attraction, okay? All right, so let's kind of summarize what we talked about. And so here's kind of an image of the size difference that we talked about. So notice how fluorine is much smaller than lithium, and notice how cesium is much larger than lithium as well, okay? So when I kind of think about the summary for atomic size, I kind of think of a snowman, okay? So as I go down a group, what happens to my size? My size gets larger, kind of like a snowman, right? So as I move down the group, radii gets larger or increases. And then think about if you have siblings especially, you've probably experienced this growing up. A sibling coming over and kind of like, hi-ya, like karate chopping down your snowman. So if I was to push down the snowman, going across the period, what's going to happen to the size? Well, when you karate chop a snowman, what happens to it? It goes, falls over, right? So as you move from left to right across the periodic table, the radii will decrease. Now, here's an important note here. This is a summary. It kind of helps you remember the trend for atomic size. My snowman image would not be accepted as a response as to why size increases going down a group and decreases going across a period. You need to remember that the reason why radii is increasing is because you're increasing amount of energy levels, where the reason why it's decreasing across a period is because you're increasing the amount of protons inside of the nucleus. Okay, so the last thing that I want you to do before you turn this video off is write down this link, which you can't see because of the glare. Let me see if I can get you to see it here. Well, that stinks. There we go. Nope. How can I get this glare off? I'm sorry. It's not working. Okay, sorry about that. This is the link to the form that I want you to complete before tomorrow's class so you can get your homework credit. Thanks for listening. See you tomorrow.